Assalamu alaikum. Good evening, everyone. Today we'll be presenting our integrated design project on the design and optimization of an industrial ethylbenzene reactor. My name is Mahmoud Ahmad, and here are my friends.
Hello, I'm Harun Mahmood.
Hello, I am Hanna Simenyo.
Hi, I'm Sally Kasaun.
Starting with the introduction, our project focuses on the industrial production of ethylbenzene through catalytic alkylation of benzene with ethylene. This process is widely used in petrochemical industries, but it comes with challenges such as parallel reactions and selectivity issues. Our goal is to analyze and optimize the reactor system to maximize ethylbenzene yield while minimizing side reactions. The main objective of this project is to perform a comprehensive reaction engineering analysis of the ethylbenzene reactor, evaluating the reaction system from a kinetic and reactor design perspective while identifying practical limitations associated with high conversion targets. We have five key objectives. First, stoichiometric analysis, which identifying the limiting reactant and expressing concentrations in terms of conversion. And then we have kinetic behavior, studying both desert and undesert reactions to understand selectivity. Moreover, we have reactor sizing, applying design equations to determine reactor volume requirements. And then we have feed composition, which is evaluating the impact of excess benzene on conversion and selectivity. Finally, we have optimal strategy, proposing realistic operating conditions that balance yield and reactor size.
Let's move on to the simulation methodology and reactor selection. To model the ethyl benzene production, we use symmetry with the Peng-Robinson equation of state to accurately handle the high pressure hydrocarbon mixture. We selected a plug flow reactor over a CSTR to simulate an industrial packed bed catalyst and to ensure zero back mixing, which would have drastically increased unwanted byproducts. We also strategically placed a preheater before this reactor to strictly control our inlet temperature without causing thermodynamic solver error. Let's move on to the reaction kinetics and catalyst modeling. The heart of our model is the kinetic reaction set. We model the primary alkylation to form ethyl benzene and the consecutive side reaction that forms our main impurity diethyl benzene. Using the Arrhenius equation, we inputted an activation energy of 50 kilojoules per mole for the primary reaction and a higher 75 kilojoules per mole for the side reaction. This effectively models our catalyst's natural selectivity towards ethyl benzene at our operating temperatures. Now, for our base case, we operate at 3000 kilopascals to maximize vapor density and collision frequency, and 250 degrees Celsius to easily overcome the primary activation energy. Most importantly, we feed a massive 5 to 1 stoichiometric excess of benzene. This heavy dilution actively starves the secondary reaction of ethylene, chemically suppressing the formation of diethylbenzene and securing high product selectivity. Before running any sensitivity tests, we mathematically validated our symmetry model. Our limiting reactant, ethylene, enters at 471 kilomoles per hour. Assuming 100% conversion, our theoretical maximum yield should be 471 moles per hour. Solver, however, produced 469.8 kilomoles per hour of ethyl benzene. That missing 1.2 kilomoles per hour perfectly matches the stoichiometry of the DEB byproduct formed. This 99.7% mass balance closure proves our reactor geometry and kinetic parameters are highly accurate.
I'll be presenting the temperature sensitivity and the pressure sensitivity analysis of our project. So, moving into the analytical core of our project, we conducted a parametric study to evaluate how inlet temperature affects our ethylbenzene production. So, the most striking finding from our symmetry simulation is the exceptional activity of zeolite-based catalysts. Even at our lowest temperature of 150 degrees Celsius, the activation energy was easily overcome, resulting in 100% ethylene conversion across the entire range up to 300 degrees Celsius. So while our ethyl benzene yield remained very stable at approximately 470 kilomole per hour, temperature does play a subtle role in byproduct formation. Diethylbenzene reached its peak at 290 degrees Celsius, showing that higher temperature slightly favors secondary undesired reaction. Um, so the real engineering takeaway here is the thermal management cost. Because this alkylation is highly exothermic, we must quench the reactor effluent using a downstream cooler. As our inlet temperature rises, the required cooling duty skyrockets, jumping from 16.4 megawatt to over 46 megawatt at 290 degrees Celsius. So operating above 170 degrees Celsius provides zero kinetic benefit to our conversion, but it imposes a massive utility penalty. So we recommend an optimal inlet temperature of 170 degrees Celsius to balance stable yield with manageable plant thermodynamics. Um, so this was our temperature analysis, and when we move into the pressure sensitivity analysis, we evaluated the effect of reactor operating pressure between 1000 and 5000 kilopascals. In many gas phase industrial reactions, pressure is a major driver of um, kinetics. However, our specific model showed remarkably such a low sensitivity to pressure changes within this envelope, which means this temperature range. So just as we saw with temperature, ethylene conversion remained anchored at 100% regardless of the pressure setting. Our primary product yield and byproduct formation both remained exceptionally stable. For instance, our ethylene benzene yield only moved between 469.6 and 469.9 kilomole per hour, while our diethylbenzene formation stayed consistently low. So why do we have to maintain a base case pressure of 3000 kilopascal? It is not to drive the chemical reaction, it's to ensure the separation efficiency of our downstream flash drum. So, maintaining this pressure is critical for managing the hydraulics and keeping the reactants in the proper phase of separation. So, this is it for the pressure and temperature sensitivity analysis.
So here we looked at the feed ratio analysis, basically how much benzene we're adding compared to ethylene. From the graph, you can see that when we add 50% more of benzene, the selectivity goes up a lot and it reaches about 97%. And the idea is actually simple. When we add more benzene, it dilutes the ethylene benzene that's already been formed. So it becomes less likely for ethyl benzene to react again with ethylene. And that's really important because that second reaction is what forms the DEB, which we don't want. So uh, by adding extra benzene, we can reduce the unwanted side reaction, which can form the DEB. And going into space velocity analysis and reactor sizing, what we did here was increase the feed flow by 2, 5, and 10 times to see how the reactor behaves. And surprisingly, even at 10 times, the reactor conversion stayed at 100%. So basically, all the ethylene that we are adding is reacting. At the same time, the ethylene benzene production increased quite a lot. it reaches above 4,600 kilomole per hour. So this shows us that our current reactor is actually too big for what we need. So the reaction is happening really fast, and so we don't need such a large reactor to minimize costs and also other expenses. So to summarize everything, first we should use about 50% extra benzene. And yes, this means we'll need a recycle system, but we think it's worth it because we can reduce the formation of the unwanted DEV. And second, for temperature, we should stay at around 170 degrees Celsius, because increasing the temperature doesn't really improve the reaction so much, and it just creates more cooling work later on. And finally, since the reaction is very fast, we think we can use a smaller reactor, and this will help us save a lot on construction costs. So overall, these changes make the process more efficient and more cost effective. Thank you for listening.